All right, everybody, what's going on? This video we have applications to physics and engineering, and we're going to look at hydrostatic pressure and force when we submerge something in water, and we're going to look at moments and center of mass. All right, so let's go ahead and get started. So the first thing we're going to look at is hydrostatic pressure and force. So it says, suppose that a thin horizontal plate with area A square meters is submerged in a fluid of density rho kilograms. This is not a P, it's rho kilograms per cubic meter at a depth d meters below the surface of the fluid. The fluid directly above the plate has volume A times d, where A is the area. So its mass, and d is the distance. So its mass is m equals rho times v, which equals rho times A times d. And the force exerted by the fluid on the plate is, the force is mg, which equals rho times g times A times d. So you need to, let me change colors here. You need to know this. This is what we have to find. All right, we've got to find the force. That's what we're looking for. All right. And so, here's your plate submerged, and they're talking about the fluid directly above the plate. So that would be, the fluid directly above like this. All right. And then it's down some depth, D. This would be D right here. All right, so let's keep reading and see what we've got. Where G is the acceleration due to gravity, the pressure P on the plate is defined to be the force per unit area. All right, so the pressure is the force divided by the area, which is equal to rho times G times D. All right, so hopefully that makes sense to you. Let me just show you here. So the pressure is equal to force over the area. Well, what's the force? The force is this up here, rho times G times A times D, which is rho times G times A times D over A. And then you can see how the A's cancel out, and you're left with just this for your pressure. All right. So we have the SI unit for measuring pressure is a Newton per square meter, which is called a Pascal. So 1 Newton per square meter is equal to 1 Pascal. Since this is a small unit, the kilopascal is often used. For instance, because the density of water is rho equals 1,000 kilograms per cubic meter, the measure at the bottom of a swimming pool, 2 meters deep, is, so here's your pressure, rho, which is 1,000, see they tell you there, all right, times G, which that's the acceleration due to gravity, which is 9.8 meters per second squared, times the distance, which the distance is 2 meters deep, and that's 19,600 Pascal, which if we convert that to kilopascal, that would be 19.6 kilopascal. All right. An important principle of fluid pressure is the experimentally verified fact that any point in a liquid, the pressure is the same in all directions. Thus, the pressure in any direction at a depth d in a fluid with mass density rho is given by P is equal to rho times G times D, which is equal to delta times D. All right, so let's talk about this a little more. So this helps us to determine the hydrostatic force against a vertical plate or wall or dam. This is not a straightforward problem because the pressure is not constant but increases as the depth increases. All right, so when you submerge that plate into water, that pressure is not the same on that entire plate. It changes the further down you go or the further up you go that, on that plate. The pressure at the bottom of the plate is more than the pressure towards the top of the plate. And then, so what does this mean here? Okay. So when using U.S. customary units, we write rho is equal to, we write P, the pressure, is equal to rho times G times D, which is delta times D. All right. So delta times D, and I wrote this wrong here. I thought it looked weird as I was reading it, but this should be delta is equal to rho times G. We're replacing this rho times G with delta when we're in customary units. When we're in, say like we had up here, when we're in SI units, we have rho times G, the acceleration due to gravity, times D, the distance. And when we're in U.S. customary units, we're delta times the distance. All right. Where delta is the weight density as opposed to rho, which is the mass density. So for instance, the weight density of water is delta is 62.5 pounds per cubic foot. All right. So we have an example here that we want to work. All right, so how do we go about this? Well, let's read the problem. So it says a dam has the shape of a trapezoid shown in the figure. The height is 20 meters. There's your height. And the width is 50 meters at the top and 30 meters at the bottom. Find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top of the dam. All right, so what do we need to find here? Well, we've got to find the force, and then we integrate it. All right, we've got to find the force. Now, what is the force? Well, the force is equal to the pressure times the area. That's the force. That's what we've got to find. Let's go back up here and look at this. See, here's your force. See, your force is equal to rho times G times A times D. All right. Well, what is pressure? Pressure is rho times G times D. See, there's rho times G times D. This right here is pressure times the area. That's your force. That's what you're looking for. All right. So let's see how we can find that. So we need the pressure and we need the area. All right. So let's set up our equation. That's what we've got to find. Okay. So what we want to do is we want to draw a rectangle here. All right. I don't care about the entire plate that's underwater. All I'm looking at is a little strip, and I'm going to find the area of this little strip right here, and then I'm going to integrate and sum all those rectangles up. Okay, so or all those strips up. So I've got a strip here, and then I would have another strip here, another strip here, another strip down here. I would have an infinite number of strips. So all I need to do is find the information for this one little strip and then integrate it from, and then I've got to figure out what my limits are. All right. So let's draw let's draw our axis right here, okay? And let's call this X. You could call it Y. It doesn't matter. I'm going to call it X. And I tell you what, in the next example, we'll call it Y to show you it really doesn't matter. All right. So what's the thickness of this strip? The thickness of the strip is dx. That's my thickness. All right. So now we've got to figure out the area of this strip. Well, what's the area of the strip? Well, the area is the width here, dx, or this thickness, let's call it thickness, dx, times the width or the length of the strip. Okay, that's how I find the area. Let me just kind of shade this in using lines. All right, so let's look at this right here. So I'm going to call this 0, and then it tells me that the water, where does it say? It says find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top of the dam. So that means it's down here 4 meters. And we'll say the strip right here, okay? So the distance from here to here of the strip, we'll call that X. And then the entire distance from here to here is 20, okay? So this would be 0, this would be 4 meters down, this would be X meters down, and this would be 20 meters down. So I need to find the length of this strip. Well, look at this. If I draw a line right here, okay, and if you look at this right here, all right, so we know that this right here, the distance from here to here would be 30, right? So that means we have 20 left over. Okay, so the distance from here to here is 30, so that means this distance and this distance would equal 20, so that means this is 10. And we will call this distance from here to here, we'll call that A. All right. So let's come over here to the side and just bring this rectangle over here. So I'm gonna just draw this rectangle. Okay, so what I did is I took this little piece here and I brought it over to the side. And here's my strip. There's my strip. So I know this distance is 10. This distance is A. Okay. And I know this total distance here, that is 20. And then this distance, well, what would that be? Well, I know that from here to here is X. We know that. Okay, we labeled that right here. So what would this distance here be? Well, this would be 20 minus X, right? And so remember, I need to get this the distance right here. So I can use similar triangles. And so that's going to give me A over 20 minus X. See, this side over this side is equal to 10 over 20 is equal to 10 over 20. And so that tells me A is equal to 1/2. 10 over 20 is 1/2. And then I'm going to multiply the 20 minus X. All right. And so that's going to give me A is equal to 10 minus 1/2 X. So there's the distance A. So now let's look at the length of the strip. So the length of the strip, we'll call that W. That is equal to what? that's equal to, let's just look at this side right here, and then we'll have to double it. So I know the distance from here to here, I know that's 15. So it's going to be 15 plus A. You see that? It's going to be 15 plus A. That's the distance from here to here. And that's just half of it. So if I double it, that'll give me the entire distance. So then I'm going to double this. And so that's going to be 2 times 15 plus A. Well, what's A? A is 10 minus 1/2 x. See, there's A. And so this is going to give me what? Well, 15 plus 10 is 25. 25 times 2 is 50 minus, and then 2 times negative 1/2, or 2 times 1/2 x is just going to give me x. So this is the width of the strip. All right. So remember, in all of this, and let me write the formula down again. The force is pressure times the area. So let's find the area of this strip. So the area is what? It's the width of the strip times dx, right? It's the width times the thickness here, dx, which is equal to 50 minus x times dx. There's the area of the strip. All right, so I've got that taken care of. Now I need to find what? I need to find the pressure. So the pressure, well, that's what? That's rho times g times the distance. Okay, so remember that was back up here. Where is it? There we go, right here. See, the pressure is rho times g times d. All right, so what is rho? Well, that's what? That's 1,000. Remember the 1,000 kilograms per cubic meter. That was back up here. Let me see if I can find it. There we go. It says the density of water is rho equals 1,000 kilograms per cubic meter. All right. So, and keep in mind that number can change depending on what kind of liquid you have. Okay, it might be some other kind of liquid that has a different weight to it. Okay, but no, water is 1,000 kilograms per cubic meter. And then we have times g times the acceleration due to gravity, which that is 9.8. So let me put that in parentheses, times 9.8, times the distance to the strip. Well, what's the distance to the strip? Well, the distance to this strip here. Now remember, they want to know the distance from the top of the water to the strip. Well, I know the distance from the top here to here is x. See, this distance here, this total distance here is x, and then if I want just this part, I need to subtract off that 4. You see that? And that will, so see that distance comes out here, so the entire distance is x, and then the entire distance is x, and then I subtract off the 4, and that leaves me with that, which is just x minus 4. And so that's times the distance, x minus 4. And now we have it. Okay? And so now I have the force, which is the pressure times the area. Okay? So that's going to be the pressure, which is, what is that? Let me multiply. All right, so that's going to be 9,800 times x minus 4. Okay, so that's the pressure times the area. So times 50 minus x times dx. And then when I multiply this out, I'm going to get 9,800 times, and then when I FOIL this out, that's going to give me negative x squared plus 54x minus 200 times dx. And so now we integrate. So the force, now keep in mind, this force that I have written here, this is the force just on that one strip. So, and you know, I guess I could put S for the force on the strip, but the total force on the plate is equal to the integral, and I'm gonna take the 9,800. I'm gonna bring it outside the integral, and that's going to be negative x squared plus 54x minus 200 dx. And now, what's our limits of integration? Well, where are we integrating from? Well, the water, okay, so that's going to be from what? From 4, you see that, to 20. I'm integrating over that water. This is the lowest, this is the highest. And so I'm going to integrate from 4 to 20. And, you know, look, I'm not going to go through all of this, but that's just 9,800 times, that's negative 1/3 x cubed plus 27x squared minus 200x, and that's from 4 to 20. And then when you punch all that into your calculator, you end up with all right, so that would be the force on the plate. All right, so I hope that made sense. I mean, it really, it's easy. It's easy to do. You just need the force, and that's the pressure. So find the pressure, and then you need the area of the strip. And keep in mind, all we're concentrating on is that one little strip. That's it. You find the area of that strip. That's usually the toughest thing to do, is finding the area of that strip. All right, so let's go to the next example. It says find the hydrostatic force on one end of a cylindrical drum with radius 3 feet if the drum is submerged in water 10 feet deep. All right, so we're in U.S. customary units, right? All right, so let's draw a picture here. So we've got the water here. All right, and we've got the end of the drum, which is a circle. Let me see if I can draw that. Maybe draw that a little bigger so we'll have room to go in there and label everything. And, you know, what I'm going to do is I'm going to draw this y-axis here. And, you know, if you wanted to, you could call it x-axis, but let's call this the y-axis. This is your x-axis. And I'm going to have the origin right here. And the reason I'm going to have the origin there is because it makes the equation of the circle simpler. I mean, yeah, if you wanted to, you could move this up here, or you can move it up here where the water is, or you can move it down here. It doesn't matter. Just try to put it somewhere so when you're dealing with this and you're coming up with an equation for this circle, try to get something that's easy. Okay? All right. So let's label this thing a little bit. Let's go ahead and put our strip right here. Okay, so that's all we're concerned with, is this strip right here. we're going to find the force on that strip, and then we integrate it. All right. So this distance from here to here, we know that's 7. And this right here, well, we'll just call that D. And then we will call this distance here to here, let's call that Y. We're going up Y units, okay? And so I need the width of this strip here. Well, once again, I'm going to look at just this half of it. And yes, I know my drawing doesn't look like it, but this distance is the same as this distance. Okay, I know it's not, doesn't look like it, but it is. All right, so what's the equation of this circle? Well, I know the radius is 3 feet, and so the equation of this circle is x squared plus y squared equals 9. There's the equation of my circle. So let's find the length of the strip. Well, this right here, that's what? That's 3, right? That's 3. And this distance here, that's y. See, we labeled it y over here. So this is just Pythagorean theorem. This is just the Pythagorean theorem. So I know, all right, so right now I'm finding the length of the strip. And so Pythagorean theorem, that's 3 squared is equal to y squared plus a squared. And so I know I get a is equal to the square root of 9 minus y. And so I know now that the width is 2 times a, right? It's twice a because this is a also. And so that's equal to 2 times the square root of 9 minus y. That's the width. So now let's get the area. So the area is the width of the rectangle, which is 2 times the square root of 9 minus y. Oh, and look at this. We didn't label this. The thickness here, let me get that, give some room there. This is dy. The thickness is dy, so that's times dy. All right. So now we have the area. Now what do I need? Well, remember, we're looking for force. Okay? So remember, force is the pressure times the area. I've already found the area. Now what's the pressure? Well, the pressure is equal to delta times D. Well, in this case, what's delta? Well, remember, back up here, it tells us when we're in U.S. customary units, the pressure of water, or the weight density of water, is 62.5 pounds per cubic foot. So delta is 62.5. All right, so delta, that's 62.5 times the distance. Okay, so how far is it submerged? We need this distance right here. Well, this entire distance is 7, and remember, to there is y. So if we go down 7 and subtract y, that will give us this distance here, which is 7 minus y. And so that's times 7 minus y. So there's your pressure. And so now we have force is equal to pressure times area. And I'm going to label that Fs, okay? Because this is just going to be the force on that strip. And so the force on that strip, that's 62.5 times 7 minus y, all right, times the area, which is 2 times the square root. Oh, and I'm sorry, this right here should be y squared. All right, so that's 9 minus y squared. All right, times dy. And so now, what do we need to do? Well, we need to integrate it. All right, so the force is equal to the integral, and I'm going to go ahead and do the 62.5 times 2, and that is equal to 125. I'm going to bring that out, and so that's going to be 7 minus y times the square root of 9 minus y squared times dy. And what am I integrating? Well, the part that's underwater, right? So I want to go from here to here. That's what I want to do. Well, this is what? This is -3, and this is 3, because remember, this is 0, and the radius is 3. So I'm integrating from -3 to 3. Now, what do I need to do? What do I need to do in order to integrate this? Well, I'm going to have to write 125 from -3 to 3 of 7 times the square root of 9 minus y squared dy minus 125 times the integral -3 to 3 of y times the square root of 9 minus y squared dy. Okay, so all I did is I took this and I distributed it to each one, and I split up the integral. And now, let's look at this. This 7 times 125, let's go ahead and multiply that together, and that's going to give me 875. All right, so let's look at this. So right off the bat, I could integrate this one pretty easy, but I know here I'm going to get 0. All right, so how do I know that this is 0? Well, if you remember, there's integrals of symmetric functions. It's back in chapter 5 if you're using the Stewart book, and I'm guessing it would probably be chapter 5 in most other books. It's back when you first started learning how to integrate. And it says that if our function in here is an odd function, and our limits are -a to a, which in this case -3 to 3, and this function is odd, then it's 0. Okay? All right. So that's just going to leave me with 875, and that's going to be from -3 to 3 square root of 9 minus y squared dy. All right, so now how would I go about integrating this thing? Well, to integrate this, we could use trigonometric substitution. Okay, you could use trigonometric substitution, and you would say, okay, we're going to let y equal 3 times the sine of theta. Okay, remember that when you did the trigonometric substitution? But we notice that this is the area of a semicircular disk with radius 3. See, this is a semicircle, right? This 9 minus y squared, that's just the top half of the circle. You see that? All right. So, well, what's the area of the circle, of a circle? It's pi r squared. So this would be the 875, and this is just the area of a semicircle. Well, the area of the circle would be pi times r squared, but since we have a semicircle, that's 1/2. Okay, it's half the area of a circle, and so that's going to leave us with 12,370 pounds. All right. But like I said, if you don't recognize this, you can integrate that using trigonometric substitution. It would be more work, but you can do that. All right. All right, so now let's look at moments in center of mass. So the moments in center of mass, I've got, let's suppose, I don't know if I can draw this very good. We'll see. I'm not very good at drawing. All right, so we've got a plate here with a point, and this point that we're looking for, we'll just call that maybe point P. So what we're looking for here is to find the point P on which a thin plate of any shape balances horizontally, like this plate right here. It's going to balance horizontally on this. All right, so this point is called the center of mass. All right, or center of gravity of the plate. So the first thing we want to do, let's look at something simpler. Okay, let's look at something simpler, where we're going to have two masses, M1 and M2, and they're attached to a rod on opposite sides of a fulcrum, and a distance D1 and D2 from the fulcrum. All right, so let's just draw that. Let's draw that picture out. Okay, let's draw the picture out. All right, so here's our drawing. Okay, so basically what we're going to have is the rod will balance if M1 times D1 is equal to M2 times D2, if those two are the same. All right, and this is called the law of the lever. So one way you could think of it is think of a lighter person balancing a heavier person on a seesaw by sitting farther away from the center. Okay, that's going to make a difference how it balances. All right, so now let's suppose that the rod lies along the x-axis with M1 at x1 and M2 at x2, and the center of mass is x bar. Okay, so let's just draw a picture of that. Okay, let's draw a picture. So if I draw that picture, that's going to look something like this. All right, and we'll say this is over here is 0. And so here I've got x1, and the mass here is M1, that's the mass. And then let's put our fulcrum here, and this would be x bar. Okay, that's the center of mass. We'll label that x bar. All right, now let's finish labeling this. So let's suppose we have x2 out here, and the center of mass there is M2. All right, so then we know that this distance here would be what? X bar minus x1. That's that distance, x bar minus x1. And then this distance here would be x2 minus x bar, right? This distance x2 minus x bar, that would leave us with this distance here. All right, so remember what that does. Remember up here, M1 times the distance D1 has to equal M2 times the distance D2. And so what we've done is we've come down here and we've just put it on the x-axis. This is our x-axis here. All right, And so we're going to call this distance 0 to x1, 0 to x2. So this would be x1, this would be x2, and these are the distances between them. And so what that gives us is that gives us m1 times x bar minus x1, right? The mass at this point times the distance it is from the fulcrum equals m2, the mass at x2, times the distance from the fulcrum. So that's going to be times x2 minus x bar. And then if we distribute, we get m1 x bar minus m1 x1 equals m2 times x2 minus m2 x bar. And so then if we solve this thing for x bar, this is going to come over. So that's m1 x bar plus m2 x bar is equal to, let's see, what is that going to be? That's going to be m2 x2 plus m1 x1. And so then if I factor out an x bar, that's going to give me x bar is m1 x1, I'm just writing this one first, plus m2 x2 over m1 plus m2. So the numbers, okay, so know this. So the numbers m1 x1, the m1 x1 and the m2 x2 are called the moments of the masses m1 and m2 with respect to the origin. All right? And what the equation says is that the center of mass x bar is obtained by adding the moments of the masses m1 x1, m2 x2. That's the moment of the masses. This is the moment of the mass m1. This is the moment of the mass m2. Okay? So the center of mass is obtained by adding the moments of the masses and dividing by the total mass. And so the total mass, we can call that m, which is m1 plus m2. All right? So let's look at this. So in general, if we have a system of n particles, okay, a system of n particles with masses m1, m2, all the way to m sub n, located at the points x1, x2, all the way to xn on the x-axis. It can be shown similarly that the center of mass of the system is located at x bar is equal to the sum of I equals 1 to n of m sub I times x sub I over the sum of I equals 1 to n of m sub I, which that is just the sum of I equals 1 to n of m sub I times x sub I divided by m. Remember, m, we said m, that's the sum of all the masses. That's what this is. All right? All right, so that's the total mass of the system and the sum of the individual moments. All right, so, and then also know that this capital letter M, which is equal to the sum of I equals 1 to n, of m sub I times x sub I. This is called the moment of the system about the origin. Okay? So in a similar way, I'm not going to spend much more time on this so we can get to these examples. But so we can also consider a system of n particles with masses m1, m2, and m sub n located at the points. So you could have n particles with masses m1, m2, all the way to m sub n, located at the points x1, y1, x2, y2, all the way to x sub n, y sub n, in the xy plane. So by analogy with the one-dimensional case, we can define the moment of the system about the y-axis to be m sub y. So the moment about the y-axis is going to be m sub y is equal to the sum of I equals 1 to n, m sub I times x sub I. And then the moment about the x-axis, which is m sub x, that would be the sum I equals 1 to n of m sub I times y sub I. All right. So what would be the center of mass? Okay. What would be the center of mass if we had a set of points, a group of points like this? Well, the center of mass would be x bar, y bar. All right, and keep in mind, this is center of mass. That would be our center of mass. And the center of mass would be x bar, y bar, where x bar is equal to m sub y over m, and y bar would be m sub x over m. Okay, and what is m sub y? What is m sub y? That's this up here. And what is m sub x? That's this right here. And what's m? M is the sum of the masses. Okay, remember that. M is the sum of the masses. See m, that's the sum of your masses, this up here. So the m, we can write that. M is the sum of the masses. I equals 1 to n of m sub I. All right, so now we're ready to work all this stuff. So I think now, this is the formula you're going to need. This is what you're going to need to find the center of mass for a group of points. So let's look at an example. So it says find the moments and center of mass of the system of objects that have masses 3, 4, and 8 at the points -1, 1, 2, -1, and 3, 2. Okay. So let's look at that and see what we get. All right, so I paused the video and wrote our formulas down. All right, so let's find the moments first. So let's find, let's see, we'll come right here and do it. All right, so we've got m y. Okay, so remember what my is. So remember, my is equal to the sum I equals 1 to n of m sub I times x sub I. All right. So look, you see this? This is m1, this is m2, this is m3. This is x1, y1, this is x2, y2, and this is x3, y3. All right. So we've got what? 3 times what? x1 times -1 plus 4 times the 2 plus 8 times x3, which is 3, and that equals 29. And then we have mx. Well, remember, mx, that's the sum of I equals 1 to n of mi times yi. So I'm going to multiply each of these masses times y1, y2, y3 respectively, okay, and sum them up. So that's going to give me 3 times 1 plus 4 times -1 plus 8 times 2, and that gives me 15. All right, so there's my m1 mx. All right, so this is what they're asking for when they ask you to find the moments. Now we want to find the center of mass. So remember, the center of mass is x bar, y bar. So you can see I've already found my, mx. I found my moments. Now I need to know what m is. Well, remember, m is just the sum of the masses. That's 3 plus 4 plus 8, which is 15. And so, all right, so running out of room here. So I've got x bar is equal to what? That's m. Let me see. Let me come up here and do it so I'll know. And let me erase this. Running out of room here. So I've got x bar is equal to my over m. See, I got it written right here. And that's equal to 29 over 15. I've got y bar is mx over m, which is 15 over 15, which is 1. And so my center of mass is 29 over 15, 1. So there's the center of mass, and there's my moments. All right. All right. So that's when you have points. Okay, that's when they give you points. All right. So what about the center of mass of just any region, like this region here? What would be the center of mass? Well, I'm not going to go through all the things of how we come to the formula and everything. That's probably explained in your textbook, so you can go look at that. I mean, we're already over 50 minutes into the video, so let me just give you this. So the center of mass, so x bar is 1 over a times the integral x f of x dx from a to b, and y bar is 1 over a times the integral from a to b of 1/2 f of x squared dx. Now what is a? A is the area under the curve. Okay, a is the area under your curve, so you know how to find that. Okay, so in other words, you would know that the area A is just the integral a to b of f of x dx. That would be the area under the curve. All right. All right, so let's look at some of these examples here, and we'll write the formula out every time we use it. All right, so it says find the center of mass of a semicircular plate of radius r. All right, so find the center of mass. We got a semicircular plate. And so, well, there's our semicircular plate. And we'll call this negative r, and this is r, because they tell us that the radius is r. And I know the equation of this semicircle would be what? Y equals the square root of r squared minus x squared. That would be the equation of that semicircle. All right. So now, place your xy coordinates, your xy coordinate system. Place that somewhere easy. Okay, this is 0 here. All right, so let's find the center of mass. So here we need to calculate x bar. And we know what the formula is, but we could plug all that into here. But I'm not, because I know that's going to be 0, okay? Because this thing's symmetrical if we go along this x-axis, this thing's symmetrical about the y-axis. So I know my point is going to be somewhere right here. I mean, it's not going to be to the left or to the right. This thing is symmetrical. I know it doesn't look like I have it drawn like that, but this thing's the same. So we know x is 0. Okay, we know that, and you could verify it. Okay, you can verify that, but we don't need to. All right, so now let's find y bar. Okay, so we know y bar is equal to, now what I like to do here is 1 over 2a. I like to bring that 1/2 out. That's a to b of f of x squared dx. Remember, the 1/2 was in here. I usually just pop that 1/2 out. You end up doing it anyway most of the time, so why not? Now for the area, for the area we could integrate this thing. Okay, we could integrate this to find the area. But come on, what is this? This is a semicircle. So I know the area is 1/2 times pi r squared, right? Because the area of a circle is pi r squared. I've got a semicircle, so that's half of that. Well, what's the radius? The radius is r, so there's my area right there. So I know A is equal to 1/2 pi r squared. And so that's going to give me y bar is 1 over, and that's going to be 2, that's this 2 here, and then times 1/2 pi r squared times the integral of f of x squared. Well, what's my function? It's the square root of r squared minus x squared, so that's the square root of r squared minus x squared dx. And then I want to integrate. How do I want to integrate? Well, I need to go from negative r to r, right? So negative r to r. All right, so this is going to give us 1 over pi r squared from negative r to r of r squared minus x squared. All right, so when I square that, when I square this, the square root just goes away, dx. Now, I can integrate this thing, but wouldn't it be easier to do this when you evaluate it? Wouldn't it be easier to say 2 over pi r squared from 0 to r of r squared minus x squared dx? See, isn't this thing symmetrical? So isn't this area right here the same as this one. So why not just find this area right here and integrate from 0 to r and then double it? That's where that 2 comes from. Okay? It makes it easier for when you evaluate at 0. Okay? And so now that's going to give me 2 over pi r squared times, and that's going to be r squared x minus 1/3 x cubed, and that's from 0 to r. And so that is going to give me 2 over pi r squared times, and that's going to be r squared times r minus 1/3 times r cubed minus, and then this is what I was talking about. We're plugging 0 in for x, so we know that's just 0. And so once I do all of this, that's going to actually give me 2 over pi r squared times 2r cubed over 3. I believe that's right. Yeah. And then I can combine those. When I multiply them, I'm going to end up with 4r over 3 pi. So my center of mass is 0, 4r over 3 pi. And there's my center of mass. All right, so let's look at the next problem. It says, find the centroid of the region bounded by the curves y equals cosine x, y equals 0, x equals 0, and x equal pi over 2. All right, so let's sketch the graph here. So we know cosine, it starts up here and it comes down. Okay, and we know it crosses here at pi over 2, and then see it just keeps going like this. Cosine does. But all we're interested in is to pi over 2. So we're just interested in this part. We're looking for the centroid. All right. So we need to find x bar and we need to find y bar. So we know x bar, that is equal to 1 over a times the integral a to b x f of x dx. Y bar is 1. Remember that 1/2, I'll bring that outside the integral. A to b of f of x squared dx. So I need the area. So let's find the area first. So the area is the integral. There's 0, there's pi over 2. So the area under this curve from 0 to pi, or 0 to pi over 2, that's 0 to pi over 2. And that's of cosine x dx. So that's going to be what? Sine x from 0 to pi over 2 is equal to sine of pi over 2 minus sine of 0, which that's what? That's 1. So that worked out pretty nice there. All right, so now let's find x bar. So that's going to be 1 over a, and we're going to go from 0 to pi over 2, and that's going to be x times f of x, which is cosine x dx. All right, and so we need to integrate this thing. Now, I would do it, but I'm not, because you should know how to do this. I'm going to leave out a few steps, but this is just equal to x times sine x from 0 to pi over 2 minus the integral 0 to pi over 2 of sine x dx. So what did I do there? I did parts, and I guess I'm going to go ahead and write it down. But remember, u is equal to x, dv is cosine x dx, so du is dx, and v, that would be, what would that be? That would be sine x, and then we write that out. And this is going to give me what? This is going to be x sine x from 0 to pi over 2. Now we need to integrate this thing. And so the antiderivative of sine is negative cosine. So that's going to be plus cosine of pi over 2. Cosine x, 0 to pi over 2. And I'm not going to go through plugging all that in. You should know, you should be able to do that by now. This is actually equal to pi over 2 minus 1. Okay, if we don't plug anything into our calculator. All right, so there's x bar. Now let's look at y bar. So that's going to be 1 over 2 times a. So that's 1 over 2 times 1 times the integral 0 to pi. And that's going to be f of x squared. So that's going to be cosine squared x dx, and that should be pi over 2. All right, now, how in the world do we work this one? Well, remember this, you probably did an example like this. If you didn't do it with cosine, you probably did it with, if you didn't do it with cosine squared, you probably did it with sine squared. And so this is going to be 1/2 times the integral 0 to pi over 2. And that is going to be what? That's going to be 1/2 times 1 plus cosine 2x dx. What did we do there? We used those half angle identities. Remember your half angle identities when you were doing trigonometric integrals? See, I'm telling you, you've got to know all that stuff that you learned back in chapter 7. Trigonometric integrals, parts, trigonometric substitution, okay, partial fractions. You've got to know how to do all that stuff. And so this is 1/4, and that's going to be 0 to pi over 2 of 1 plus cosine 2x dx, which when we integrate that, that is going to give us 1/4 times, that's going to be x plus 1/2 sine 2x, and that's going to be from 0 to pi over 2. And I'm not going to go through and plug all that in. You should know how to do that. And that would give you pi over 8. So there's your x bar, there's your y bar. So the centroid, that is pi over 2 minus 1, pi over 8. And there's your answer. Okay. All right, so let's look at this. This is the last example. So if you're still watching, I'm glad you hung around. I know this is a long video. All right, so here they want us to find the centroid of the region bounded by the line y equals x and the parabola y equals x squared. So let's draw this. There's the parabola, and here's my line. And I know I've exaggerated it a little bit, but this is what we're looking for, this region right in here. Okay, so this is a little bit different, but you shouldn't have any problem with it. So the centroid, it's the same thing. It's the same thing as before. Okay, it's the same thing as before. Remember, this is y equals x, and this is the curve y equals x squared. So it's the same thing as before. It's just what we've got between two curves, an area between two curves. Well, you know how to do that. You learned that back when you had a section on finding the area between two curves. And remember, the area was the function on top minus the function on bottom. And so x bar here, that would be 1 over a times the integral a to b of x times, and that's going to be f of x minus g of x dx. Okay? And keep in mind that f of x is greater than or equal to g of x. And then y bar is 1 over a, okay, times the integral a to b of 1/2 times, okay, times f of x squared minus g of x squared dx. And then, of course, the area, we know how to find that. The area would be the integral a to b of f of x minus g of x dx. All right, so let's do it. So we've got a is equal to the integral a to b. And so we know we're going from 0. We got to find out, where does that intersect? Well, where do these two functions intersect? Well, that's when x squared is equal to x. And so x squared minus x is 0. X times x minus 1 is 0. So x equals 0 or x equals 1. So we're integrating from 0 to 1 of f of x, which is x, minus g of x, so minus x squared dx. And there's no sense in me working that out. You should. That's very simple to integrate and evaluate. If you can't do that, then you probably won't be very successful in your calculus class. Okay, you should be able to do that by now. Now, I'm not trying to be ugly when I say that. All right, so now let's find x bar. So that's 1 over 6 times the integral, and we're going from 0 to 1 of x times f of x minus g of x. Well, we've got f of x, which is the function on top, that's x, minus g of x, the function on bottom, times dx. And so this is going to give me 1/6, 0 to 1 of x squared minus x cubed dx. And then we have to integrate that 1/6 times 1/3 x cubed minus 1/4 x to the 4th from 0 to 1. And then you evaluate that and you end up with 1/2. So there's x bar right there. Okay. And now let's look for y bar. Well, that's 1 over 2. Okay, so where's that 2 coming from? Remember, I'll take that 2 and bring it out. So there's the 2 times the area, a. So times 1/6. And that's from 0 to 1 of what? Of f of x squared. So that's x squared. You see that? That's the function on top, which is x, and then I squared, minus the function on bottom, squared. So minus x squared squared, and then dx. And so this is actually going to be, this is going to cancel. That's going to be a 3. 1 over 1/3 is 3 times the integral 0 to 1 of x squared minus x to the 4th dx, which that's going to be 3 times 1/3 x cubed minus 1/5 x to the 5th from 0 to 1. And that ends up giving you 2/5. All right, so the centroid is 1/2 2/5. And there's your answer. All right, so I hope that video helped. I know it was a long one, but hopefully you learned something. Look, these things really aren't that hard. The finding the centroid, the center of mass, that's those problems are pretty easy. The ones that are probably the more difficult ones is finding the hydrostatic pressure or force. But remember, they're easy to do. I mean, it's just forces. That's the pressure times the area. That's all you got to find. Okay, and just use the formulas that you're given. So I hope this helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I'll see y'all in the next one. Later.